Everyone. Today we're going to talk about organizing and interpreting data. We're going to use our Venn diagrams to be able to count how many items are in a set. Now this is useful when you collect survey results. Okay, we want to organize them so we can analyze the data. And Venn diagrams and organizing really helps us to do this. So the first thing we're going to do is look at a warm-up. I have the sets here of favorite sports to watch, and I picked a few sets. I picked hockey, basketball, and football. Now I placed my name somewhere. I want you to take a second, maybe pause the video, think of where would your name go, and what would that mean? Okay, now that you've unpaused the video, I would go here. Okay, I put my name down here because my favorite sport is football. Now, there are people that probably put their name in the middle, which means they like hockey and basketball and football as their favorite. There's people that would maybe have two favorites. Or maybe you don't like any of these sports as your favorite. Maybe you like soccer, golf, or tennis, baseball. Okay, so we still have a universe of a whole bunch of other sports. So there are always multiple sets. Maybe you fit in one or the intersection of two of them or the intersection of all three of them. Now today we got to remember that an element is a single entry. So in the warm-up, I was an element. You were an element. The union was I belonged in at least one of the sets, and the intersection is where two or more of the sets met. Now today we're going to focus on the cardinality. How do I count how many elements are in a set, or part of a set, or in a union, or in an intersection? So the cardinality is the number of elements, is the count. How many elements are in that set? So if I gave you a set with the elements 2, 4, and 6, I would say the cardinality is 3. So the number of elements in set B is 3. And this is the notation that we use. Generally, it's more important to know how many elements there are in a set than exactly what they are. So this just tells me that there's 3 elements in the set, and I can use that information. So now an example is we have two sets, set A and set B. Set A contains 25 elements. Set B contains 17 elements. There's 9 elements in the intersection. They're common to both sets. And I want to know how many elements I have total in this whole situation. Now, this seems easy. It seems, okay, I got 25 elements here and I have 17 elements here. 25 plus 17 is 42 elements. But we're about to see that that is not the case, because this 9 elements that are in both are going to kind of change where these numbers look on a Venn diagram. So I always recommend creating a visual. So we have the universe, we have elements that might be outside of set A or B, set elements that are in the intersection, or just one or the other. Now the problem tells me that I have 25 elements in set A. Set A is this whole circle. So either in this or this region. Now, I can't just put 10 and 15 or 9 and 16 or 5 and 20. I need to figure out exactly what one of these regions is. And this is where the intersection is going to be helpful and probably what I'm going to do first. So it says 9 elements are common to both. So I have 9 elements in the intersection. And now I know that x plus 9 is 25 elements, so I can calculate A. So A is 16 elements in only A, not in the intersection. And I can do the same process with B, where set B has 17 elements, so 9 plus something is 17. So there are 8 elements only in B. And now I can count that there's 16 only in A, there's 9 in the intersection, and there's 8 in only B, which makes 33 total elements. So the cardinality of A union B is 33. There are 33 elements in at least one of these circles or both. Now, some people like creating fancy formulas, so let's look at how this formula acts. So to find the number of elements in the union, we could take the number of elements in A, add the number of elements in B, and subtract the intersection, because this 9 is counted twice. The 9 elements that are in A also are shared in B. So we could do 25 plus 17 minus 9 is 33. But I strongly recommend set up the Venn diagram, organize our numbers, and take it one step at a time. Now, this situation also applies if we're doing 3 sets or 4 sets or 5 sets. So we're going to look at this example. Okay, we have faculty and graduate students at the University of Florida's Film School voted on which of the Three Stooges they admire. Now, if you don't know who the Three Stooges are, I'm kind of disappointed. I recommend you look them up, Larry, Moe, and Curly. And then we can continue on with the math. So here we're going to set up a Venn diagram with 3 circles, 3 overlapping circles. Now, if you want to try this problem out, pause the video, try it out, and then resume it when you feel that you got it right. So it says here, lots of information. 51 admire Mo, and 49 admire Larry, and 32 admire Larry and Curly, and 36 admire Mo and Curly, and 24 admire all 3. So where do I start? If I just want to start with just Mo, I have 4 different regions which have to add up to 51. So that's too many. If I want to do Mo and Larry are these 2. So still got too many. So I always start the most intersecting region. So all 3 have an overlap. And it says 24 admire all 3 of the Stooges. So I'm going to put 24 right in the middle. And then I'm going to work backwards. Sometimes I like to cross off the data once I've used it, so I don't worry about using it again. Now it says 34 admire Mo and Larry. So Mo and Larry are these 2. Okay, both of these circles both these regions are in the Mo and Larry circles. So 24 plus something is 34. And I can do the same thing with the other 2 regions that have an intersection of 2 circles. So Mo and Curly and Larry and Curly, I can fill in using the 32 and the 36. And now I can work back to the individual who only likes Mo and who only likes Larry and who only likes Curly. So 51 total like Mo. So 4 numbers add up to 51. So the missing number is 5. So 5 like only Mo. And I can do the same thing with Larry and Curly. And I get 7 like only Larry and 16 like only Curly. And maybe there's students or faculty that don't like any of them, and we could have a cardinality out here. In this case, we do not, but sometimes we need to look at how many people like none of the Three Stooges. Now, the first question that we have to answer is how many people were surveyed. So we can add up all of these different regions, and we get that 82 people were surveyed. Now, how many like Curly alone? So Curly, but not Larry and not Mo. So we have the Curly circle, Curly set. We get rid of anything that's Larry or Mo, and we're left with just 16. So 16 people like only Curly. Maybe the question asks a union question. How many like Larry or Curly or both of them? So Larry or Curly or both of them is anything that's within a Larry or Curly circle. Could be in one set, could be in both sets. So it's all of these numbers. So the way I calculate it is we know that the total is 82 and we can subtract 5, or you can add up all of these numbers and get 77 like Larry or Curly. Now a question could ask, how many people like exactly 1? So 7 people like only Larry and 16 like only Curly and 5 like only Mo. We could add those up and we get 28, like exactly 1, or exactly 2, which is where two circles overlap, which is the 8, the 12, and the 10. So as we do these, if we set up the Venn diagram, we can count cardinalities. We can look at two intersections or three intersections, or a circle, or the part of the circle that's by itself or outside. We can look in the universe, the rest of the universe. Maybe someone, once again, doesn't like Larry, Moe, or Curly, don't like the Three Stooges, but that's their own prerogative. So I recommend you try this problem. You create the Venn diagram. You find the cardinality of the intersection and the union, and you set it up and you organize. And with this practice, you're going to understand how we use Venn diagrams to count the cardinalities of sets.